Hey everybody. So this is the end of the spring 2021 semester, and me teaching chem335, organic chemistry 2. And I was looking at the old review session I made in the spring 2020 semester, when COVID kind of just started and we're all locked in our houses. And it turns out that the review session is exactly the same, and there's not really any reason to record a fresh review session. So I'm just going to give you guys the old review session, and all the material's the same, and all the kind of review topics are relevant. So I'll provide additional details on what's going to be on the quiz and maybe some practice problems and stuff like that on the iLearn site. So without further ado, here is the spring 2020 Chem 335 Organic Chemistry 2 review session. Hey everybody, I am excited to give you this review session. I've done this a few times for the previous semesters of students, and I think it's really useful for some of the cumulative components to sort of see a bird's eye view of organic chemistry. And yeah, there's going to be some cumulative components on the exam, and you can look in the iLearn site for more information about that. I think I'm going to give you some example multiple choice cumulative style problems. Hopefully this presentation will be useful, and I'm still around for a couple days for you can ask me questions by email. We also have that Tuesday office hours, and then the final exam is on Tuesday night, I think 5 p.m. All right. Okay, so what are we going to talk about? And actually, what should you study? I guess this presentation will be mostly focusing on reactions, things like NMR. Probably not going to have physical properties on this exam, but things like NMR are not going to be presented here because you already kind of know it, and you'll just have an NMR problem and you have to be able to do it. If you still are struggling with NMR, you need to contact me, and I can, we can try to do a sample problem or something. Also look at the quizzes where we've done NMR problems recently. For the most part in this review session, I'm not showing mechanisms and reagents, and the idea is that you can go through and do them later and review them, right? So this is a good review method. All right, but what I'm trying to do is show all the reactions in maybe a different organization than they were presented in class. Mechanistically interesting mechanisms might have a 1 star if it has a very mechanistically interesting reaction. There might be 2 stars, and so the things that don't have any stars on them you might not think of as like maybe I should review that mechanism. Fortunately for you guys, having this exam being open note helps. So it's not necessarily memorizing mechanisms, but it's organizing your notes in a way that you can find mechanisms pretty quickly if you need it, because there will be a couple mechanisms on this exam. On the exam, obscure reaction conditions can be abbreviated as oxidation or reduction or protection or deprotection. And so if it's an obscure oxidizing agent, like I think aromatic amines are oxidized to aromatic nitro with it's an MCPPA derivative, for example. I can't even remember it. Obscure oxidations, for example, can be abbreviated as bracket O bracket. For you guys with an open note exam, this is maybe not as important, I guess. But yeah, I mean, we try to emphasize that not memorizing crazy reagents that do obscure reactions, but really just emphasizing strategy, synthetic strategy. And for an obscure condition like an oxidation or reduction that has a weird reagent, you can always abbreviate those as bracket O bracket. Okay, so what are we going to talk about? We're going to talk about CC bond formation, all the different ways of forming CC bonds, CC bond cleavage, and there's not as many ways to cleave bonds in organic chemistry. Functional group interconversion, so ways to transform one functional group into another, and we've seen lots of these, I guess, and it's just another class of reactions to know about. Homologation and degradation. So some of these will be a little redundant with other things, but homologation and degradation is kind of its own category, and that means kind of like adding 1 or 2 carbons to a molecule. Degradation means loss of carbons. Okay, that's often homologation would typically be an example of CC bond formation, and degradation would actually be an example of CC bond cleavage. So there's a little bit of overlap here, but I like to just reiterate homologation and degradation in its own little section. Protecting group manipulation. What are the protecting groups you know? How do you put them on? How do you take them off? A little bit about aromatic chemistry. Electrophilic aromatic substitution reactions. We can kind of review them. You can recall the reactions and mechanisms. Sandmeyer reactions, which are its own little class of reactions that you just kind of learned recently. And then we just have a section called reactions with strange mechanisms, and these also overlap with a couple of the ones above, but I just thought it'd be cool to make a little section with all the reactions that have kind of weird mechanisms. All right? Okay, so CC bond formation. Where do we start with CC bond formation? The first thing we're going to talk about are nucleophilic carbon reactions. So organometallic reagents. How many different kinds of organometallic reagents do you know? What metals are there? And this actually begins in organic 1, right? So you knew about Grignards, the magnesium, right? RMGBr. And those are actually very similar in reactivity to organolithiums, RLI, right? So Grignards and organolithiums are essentially, you just consider them same reactivity. But are there any other metals that you learned about? Are there weird metals that do CC bond forming reactions? And the answer is copper, right? So copper is like a oddball one that's a little different than the others. Okay, then we learned about enolate alkylation reactions. So different ways to attach things to enolates. That is a nucleophilic carbon reaction, and we'll review those methods. Direct alkylation, enamine alkylation. I think the acetoacetic ester synthesis, malonic ester synthesis, those kind of recent ones, you know. Alkynes. We know of alkynes as being nice nucleophiles because we can take off the proton from an alkyne and attack stuff, right? Acyl anion chemistry. That's kind of a new one that we just learned recently, and it's using thioacetals, the sulfur things, as nice nucleophiles. Okay, and then we have another section for CC bond forming reactions, carbonyl condensation reactions. So these are things like the aldol reaction and the claisen condensation, etc. So the aldol is one. The claisen, kind of a newish one for you guys. There's something called the ketone mixed claisen, which is a variation on the claisen. It's just, remember, a claisen is a reaction of two esters, where it could be a diester, like an intramolecular claisen. The ketone mixed claisen is usually a ketone and an ester, and they react, and you get a different product. Actually, what are the products of an aldol? Product of an aldol is an alpha beta unsaturated ketone, right? Product of a claisen is what? Product of a claisen is a beta ketoester, right? And then a ketone mixed claisen is a beta diketone. And then we also learned about the Michael reaction, which the Michael reaction creates 1,5-diketones or 1,5-dicarbonyls. 1,5-dicarbonyls. And then the Robinson is kind of this weird thing that does a Michael and then followed by an aldol. And it gives you an aldol product. So it's usually a cyclic alpha beta unsaturated ketone. Okay. Oh yeah, and like for this PowerPoint and the way we're delivering this remotely, you might want to. I'll put the PDF file online, and you might want to use the PDF file and maybe take notes if you're able to do that, or you could print it. It's a lot of pages, but maybe take notes and write in the reagents and the various things that'll help you to make this a good study guide for you. Okay. All right. So let's start with Grignards. All right. So this you started learning about this in Organic 1, and ketones and aldehydes react with Grignards. And so what would be the Grignard in this case? It would be phenyl Grignard, right? PHMGBr would attack the ketone and give you a tertiary alcohol. Esters react also with Grignards, but they react twice. So an ester, this cyclic ester, this is called a lactone. Cyclic esters are called lactones, LACTONES. It reacts once, and that kind of opens up, and you get a ketone. And then it reacts a second time, and you get a tertiary alcohol. Okay. Acid chlorides also do that with Grignards, and we call that R minus 2 equivalents. So this is also R minus 2 equivalents, right? Because Grignard is attacking twice. You can't attack once with a Grignard onto an ester. There's no way to attack once and stop with a ketone. That's not a possible reaction. Okay, and the reason why is why can't you just have a Grignard attack once and stop? Well, the problem is once it attacks once, because the ester is a little bit of a slow electrophile. It's not a fast electrophile. So if the Grignard attacks once, now the ketone's actually a better electrophile, so it's more likely to react a second time. There's no way to just be like, oh, well, I'm just going to throw in one molecule of Grignard and make the ketone. It doesn't work. You get a mixture of compounds. Okay? But with acid chlorides, remember there is a way to add a 1 equivalent of an R minus, and that's using a cuprate. Because the cuprates, the copper things, will attack acid chloride once, and you get a ketone out. Okay, then we also learned in this course that nitriles react with Grignards. So like phenyl MGBr, and that gives you an intermediate sort of imine-like thing, IME, imine, and that hydrolyzes with water or like acid water to give you the ketone. Okay. All right, and the mechanism is really easy, right? The Grignard attacks, electrons go up, and then usually with like H3O, this can get protonated twice. So you have 2 protons and a plus charge, and then water just attacks and proton transfer kick off. Okay. All right. Then of course epoxides react with Grignards, and they open up from the least hindered side. So they attack from the right side. Phenyl MGBr would attack from the right side and give you this secondary alcohol. How would it be different if the Grignard would attack like this aldehyde? It would actually give a product that kind of looks like this, right? Except if the same Grignard, a phenyl MGBr, would attack this aldehyde, it would attack from this right side, and the product would look the same as this, except the OH would be right there. Okay. And then how do we make epoxides? MCPBA, right? MCPBA is the way that alkenes are converted to epoxides. Right, and we'll talk about that in the functional group interconversion section. FGI, functional group interconversion. which converts, in this case, an alkene functional group to an epoxide functional group. How would you do this? How would you go about this sequence? Well, you have 2 carbons OH, and you want to make 3 carbons OH. How many carbons are we adding? 2 plus X is 3, X equals 1. So it looks like we're adding a single carbon electrophile, right? What's your single carbon electrophile? How many single carbon electrophiles do you know? Well, you know about CO2, but that makes carboxylic acids. The single carbon electrophile you'd use here is maybe an aldehyde. It's formaldehyde, right? C double bond O, and then 2 H's. So how would you accomplish this? Well, there's no magic way to do this, right? You gotta make a Grignard and then tack formaldehyde, right? OHs don't make Grignards, right? What you have to do is convert the OH into like a Br, right? So PBr3 makes a Br, right? PBr3 is how you make bromides. And so alcohol plus PBr3 makes the bromide of this, and then you do Grignard and Mg, and then the Grignard attacks formaldehyde. Okay, so you can fill that in. Okay, so what about this? Looks like we have 1, 2, 3, 4. So this, we're adding 2 carbons to 4 carbons. So we're adding a 2 carbon piece, and the big thing is, it looks like the hydroxy group is on the distal carbon, right? So that's the bond we're making. So which electrophilic functional group should we use? Which electrophilic functional group should we use? Well, it shouldn't be a ketone. Should not be an aldehyde, because if it was a ketone or aldehyde, the hydroxy group would be right there, right? It's not a ketone, not an aldehyde. What other ones do we know? Well, we know Grignard, nitriles, but that gives you a ketone, so not that. Okay, so not a ketone, not an aldehyde, not a nitrile. Maybe epoxide, yeah. So a 2 carbon epoxide. If we turn this into a Grignard the same way, and then attack the 2 carbon epoxide, kind of like this, but only 2 carbons, then that would give this product. Okay. So what we're doing here, and what I'm trying to have you practice, is like which electrophile to use to get the desired outcome. Okay. All right. So now we have 2 carbons, and we're forming a carboxylic acid. So maybe a single carbon electrophile that creates a carboxylic acid. Well, we have a great single carbon electrophile that you learned in this class, right? Well, we learned about formaldehyde, but we also can use CO2, carbon dioxide. Carbon dioxide, let's move this up here. Sorry, guys. I'm learning this recording software right now as I'm using it. And I can move my little picture around. Okay, so that might help. Yeah, we're going from a 2 carbon alcohol off the ring to a 3 carbon carboxylic acid. And the question is which electrophilic functional group to use, and the answer is CO2, carbon dioxide, right? Okay, so what if you're out of CO2? How could you do this? You're all out of CO2, but you have a big bottle of formaldehyde in the reaction in your laboratory. Well, you could do the same thing here, make a alcohol to bromide, bromide to Grignard, Grignard attack formaldehyde, kind of like we did over here, and then you'd make a primary alcohol, and then you could just oxidize the primary alcohol to the carboxylic acid. And we learned how to do that. That was with what? How do you oxidize a primary alcohol to a carboxylic acid? Think about oxidation reactions, and first you might think, PCC, right? So if you have an aldehyde and you're trying to go to an alcohol to a carboxylic acid, PCC won't work because alcohol reacting with PCC would give an aldehyde. So in this case, you have to use a stronger oxidation conditions, and you do CrO3 acid. Okay, so it would be alcohol, convert the alcohol to a bromide with PBr3. Okay, and then make a Grignard, and then attack, in this case, formaldehyde, we're saying, to make a primary alcohol, And then the primary alcohol we could oxidize to the carboxylic acid with CrO3 acid. Okay, cool. Okay, let's move my picture down. All right, cool. Okay, so moving on to other CC bond forming with organometallics. We learned about cuprates and how copper reagents like phenyl, there'd be phenyl 2 copper lithium, phenyl 2 pH2 CuLi would be a nucleophile, and it's basically a different phenyl minus. So it's a phenyl minus that would attack the alkene here, push electrons up and make an enolate onto the oxygen, and then you'd provide a proton, and then you'd be left with the ketone. So and we call this 1,4 addition because the why do we call it 1,4? It's one. It's start from the oxygen. 1, 2, 3, 4. Right. 1, 2, 3, 4. That's why we call it 1,4 addition. Amines do this also. Amines do 1,4 additions. So if you react this with like ethylamine, 2 carbons and H2, it would also attack 1,4 style. What's it called if you attack, like right there? What if you actually attack the ketone position? That'd be called a 1,2 addition. 1, 2, 1, 2, right? So that's the difference between 1,4 addition and 1,2 addition. Okay, and the other thing about cuprates is they also react with acid chlorides to give ketones. So they don't react with things like esters or amides or anything. It's really just acid chlorides, and that gives you a single addition of a R group, right? Okay, so these are the main uses of cuprates in chem335. There's other uses, but this is what we talk about. Okay, and then we also learned carbonyl alkylation reactions, a couple of them. These were kind of recent ones that were, we call them well-behaved carbonyl alkylation reactions. So the malonic ester synthesis and the acetoacetic ester synthesis. So the malonic ester synthesis, you start with a malonic ester, which is called dimethyl malonate. The idea, as you recall, and you know, you have to review this obviously yourself, is that we use a base, we take off a proton, and then we can attack something, because these are highly acidic positions, right? We take off the CH, we can attack something like an R group, and then do it again, and then we do that whole process where we hydrolyze off the esters, and then it loses CO2, and you make a substituted carboxylic acid with 2 R groups on it. Well, you can do the same thing with the acetoacetic ester synthesis, attach 2 things, and then you only have 1 ester. So we wipe off that ester, and then that decarboxylates, and you get a substituted methyl ketone, right? All right, so you got to know the intermediates and the mechanisms of all that. But that's kind of recent, so probably something you do know if you've been watching the video lectures. Okay. These are kind of other ways to alkylate things, and you learned this early on, that you could just take a ketone and attach an R group, and you could do this with a strong base like LDA. LDA would take off the proton, make an enolate, and then attack a alkyl halide or something. You know, the problem is you'd maybe get some double alkylation, some kind of a extra thing going on. And what we learned at the time was that you could kind of accomplish the same thing by making an enamine, and that's just all you use is a secondary amine, like the NH version of this, right? Maybe a little bit of acid, and that makes an enamine. You know the mechanism of that. And the enamine happens to be a pretty well-behaved, nice, happy nucleophile. So equivalent of kind of what happens if you take this ketone and hit it with LDA, you get an enolate, LDA being a strong base, right? But the enamine is also a pretty nice nucleophile, kind of like a gentle enolate. And so then you throw in a alkyl halide or something, and then the enolate looking thing or enol looking thing reacts, kicks down, attacks, and then you get your thing, this species. And then how do you go from the C double bond N to ketone? Water. So water would just attack and do some electron pushing and break this thing off. Okay, so this is called enamine. What's this thing called? It's kind of like what you might call an imine. Imines are if you have carbon double bond N without a charge, it's an imine. What's it called if you have a imine-like thing but with a positive charge? It's called an iminium. Iminium, right? Okay, so yeah, enamine, iminium, and then you have a substituted ketone. And this is, maybe we could call this the enamine method of alkylating a ketone. The enamine method. Okay, other reagents, mechanisms for these reactions, and definitely if I say star or 2 stars, that's an indication that the mechanism might be important. Alkynes are great ways to make CC bonds. We learned that early in the course, that you could rip off the proton, because the terminal proton of an alkyne is kind of acidic. I forgot the pKa, 20, 25-ish. Maybe 30. I don't remember. But the point is that it is accessible to a base. So a base can take off the proton, and then you can attack an electrophile and make an alkyl halide like this. Sorry, you can make a alkyne like this. Yeah. The other thing you can do is rip off the proton and then attack something else. What are we attacking in this case? Which electrophilic functional group are we attacking? There's the bond. That would be the squiggly line point. Ketone, aldehyde, epoxide, CO2, nitrile. What are all the things we can attack? And the answer in this case is aldehyde. So it's a 2-carbon aldehyde, right? Acetaldehyde. Okay, so what about this one? Base. Yeah, the bases are usually is butyl lithium, 4 carbons lithium, super strong base. Or I think they were using NaNH2 in this chapter. Na plus NH2 minus. Both of those are acceptable bases. Okay. And yeah, in step 2, in this case, the bottom one, there's your attachment point. The big difference is the hydroxy group is on the next door carbon. So ketone, aldehyde, epoxide, CO2, nitrile. What's it going to attack? And the answer is epoxide. So the way you know it's an epoxide is because the hydroxy group's on the next door position, right? Acyl anions. This is kind of a new thing for you guys. Which one of these is a valid idea? So take the acetal functional group and treat it with butyl lithium, rip off the proton, make a dot dot minus, as opposed to a thioacetal, rip off the proton and you make this, and then you can attack stuff with it, and then you have basically a protected ketone, right? Because this after you attack something, this is a protected ketone, right? Which one of these is valid and why? The answer is that the sulfur one, you can expand the octet, right? So you can go above 8 electrons. Oxygen you can't. So you can't violate the octet rule, and this left one doesn't work. But that's why we use thioacetals. Okay, so here's an example, acyl anion equivalent example. So take an aldehyde, make the thioacetal. We use zinc chloride as our Lewis acid. Make the thioacetal. And then we can rip off the proton. These are all 2-step processes. I think actually, well, the top's a 2-step process. At the base, maybe butyl lithium. and then maybe an alkyl halide type thing. So the BrCH2, and then it's called isobutyl bromide. Isobutyl bromide. Okay, and then in this one, it looks like we're forming a have a hydroxy group, and maybe it's an aldehyde. And then this one, it looks like since the OH is on the next door position, maybe this is an epoxide. Okay, cool. More. You can actually start with this kind of pre-made, and this is a purchasable item that you can purchase. Practically speaking, well, you go back to the previous slide. One problem here, practically speaking, is this stuff stinks pretty bad. So you gotta be a little careful with your lab technique. Otherwise, if you get this on you, you're gonna stink for a week. And I think if you ever spill sulfur things on you and you stink due to the sulfur thing, just so you know, the trick to avoid that, and this actually happens for biology people too, because there's some chemicals like beta-mercaptoethanol, thioerythritol, I think it's called. There's some biology chemicals that have thiols on them, and if you spill it on you, your friends are going to hate you. And if anyway, so the trick is to go swimming, because swimming in bleach water will oxidize the sulfurs, and not bleach water, but chlorinated swimming pool water will oxidize these things, and when they oxidize, they don't stink. So that is a trick if you ever spill sulfur things on yourself. Okay, so yeah, back to the second example. So this thing you can kind of purchase pre-made, and this does not stink. This is actually convenient. So you can treat it with a base and then like attach a first thing like propyl bromide or something, and then you can do your other things. You can maybe attach a different alkyl halide, or you can attach an aldehyde or an epoxide. And then there's the other things you can do are to get rid of the thioacetal. You can either deprotect it with a water, I guess, but you also need a metal, right? And you don't use acid for thioacetals. You don't use H+, you use a metal, and it's not zinc, it's the other one. It's mercury, HgCl2. So mercury chloride deprotects these guys, and you get the ketone. Okay, so and then there's another route you can do with the thioacetal to remove the thioacetal part, and that's H2 Raney nickel, RANEY. Okay, so it's kind of like we have two ways of kind of terminating a thioacetal reaction sequence. Okay. Let's talk about the aldol reaction briefly, review it, and review what kind of products you make with the aldol reaction. So the aldol reaction creates alpha-beta unsaturated ketones, also potentially alpha-beta unsaturated aldehydes as the product. These are just a couple examples of the different types of aldols that you learned. So if a ketone or aldehyde reacts with itself, then you first make a beta hydroxy ketone, beta hydroxy, and then it loses water. So when it loses water, so it's essentially the proton there and the OH right next door, that gives you the alpha beta unsaturated ketone product. It's called a simple aldol. And let's see. And what if you're reacting with like a ketone and then maybe another ketone or maybe another aldehyde or something like that? What would that be called? This is like a simple aldol. This is called a mixed aldol, the second one. And in this case, you got to figure out what the other piece is. You can use basic arithmetic, so it's going to be 3 plus X is going to be, there's 3, 4, and there's benzene is 6 carbons. So it's 3 plus X is 10, right? 3 plus X is 10. And is that right? 3, 4, yes. Okay, 3 plus X. Did I do that right? 4 plus 6. Yeah, that's right. Yeah, 3 plus X is 10, and so X is 7, right? And so 7, so it's going to be a benzene and then 1 carbon, and you could basically deduce that it's benzaldehyde. So it's going to be, and the other way to know that is we just take draw a squiggly line right there, and that kind of shows you what the right side piece is going to be. It's going to be not an alcohol, not benzene and then alcohol, but benzene and then it'll be the aldehyde, because the aldehyde is what's attacked. You know, this is a reaction between ketones and aldehydes. Okay, so yes, this would attack benzaldehyde, so benzene, aldehyde, and that would make the beta hydroxy ketone. Loss of water gives you the alpha beta unsaturated ketone. All right, and then we also have the intramolecular aldol, which is the one that forms between like cyclizes like this. Okay, and it's the same exact thing, same exact mechanism. So a base takes the proton, makes an enolate, right? And all of these are like, you start with the base, take a proton, make an enolate, then the enolate attacks another ketone or aldehyde, and then you get the the beta hydroxy carbonyl. Yeah, and then you lose water. So in this one, it's like your base takes proton, makes an enolate attacks, and then you get the beta hydroxy ketone. Loss of water gives you the alpha beta unsaturated ketone. And then what about doing an aldol product via retrosynthesis? How might you do this? I mean, looking at this molecule, the way to do it is you envision, you know, what would the beta hydroxy ketone look like of this? Well, there's the beta carbon. So what you would do is you'd envision a hydroxy group right there, and then you can break it apart and be like, well, this ketone, left side ketone, reacts with this would be an aldehyde. So you envision the C double bond O aldehyde, okay, to give you this product. All right, so let's talk the claisen. Let's talk about the claisen condensation, which is, you could say, vaguely similar to the aldol. It's just, it uses esters instead of ketones and aldehydes. So beta keto esters are the products of the claisen reaction. These are kind of 3 of the simple examples you are probably familiar with. If an ester reacts with itself, so it's usually going to be a base followed by acid. But the ester becomes a nucleophile, enolate, and attacks the other ester, kicks off the ethoxy, and you get a beta keto ester. Okay. That reaction where the ester enolate nucleophile attacks the other ester is called, and the electrons go up, electrons go down, and then it kicks off ethoxy. What was that called? It was 3 letters. 3 letters. It was NAS, nucleophilic acyl substitution. And that was one of our previous chapters, 19 or I think it was 19 or 20, I think, I don't know. Nucleophilic acyl substitution. And that is that's the mechanism of the claisen, okay? And then you can also do a mixed claisen where you have 2 different components, and one's going to be the nucleophile, one's going to be the electrophile. The nucleophilic one's always going to have the alpha CH, so this one has an alpha CH, and this one would react with the one that does not have an alpha CH, right? There's no alpha CHs next to the ester because the benzene is there, and the benzene doesn't have any CHs there. So this would kick off the ethoxy, and you'd get this product of the mixed claisen. And then the intramolecular claisen, it's like you have two esters and one reacts, kicks off the other ethoxy group. So they're all the same mechanism. And the intramolecular claisen is also called the Dieckmann cyclization. That's another name for it. Beta diketones are the products of the ketone mixed claisen. So the ketone mixed claisen is the same thing except it's a ketone and an ester. Yeah, so cyclohexanone might react with this simple ester. And who's the nucleophile, who's the electrophile? Well, I mean, obviously it looks like the ketone was the nucleophile because the ester part lacks its ethoxy group, so it must have gotten that kicked off. But the way to know, well, the way we kind of know that the ketone is going to be the nucleophile is if you consider the pKa values. A ketone pKa is roughly 20, an ester pKa value is roughly 25. So 20 versus 25, who's more acidic? Yeah, the ketone is. And so the ketone's more acidic and it's going to be more reactive as a nucleophile. And here's another example. And so is an intramolecular ketone mixed claisen. And well, it looks like this. Well, we have two options, I think. Which side of the ketone is going to be reactive? So if this left side of the ketone reacts, what's the size of the ring? It's 1, 2, 3, 4, 5, 6. Oh, well, okay. Well, that makes sense. Six member rings are favored, right? So, yeah. So I think this is going to react, and it's going to make a 6-member ring. 1, 2, 3, 4, 5, 6, as opposed to the other side, which would be 1, 2, 3, 4, 5, 6, 7, 8. 8-member rings are kind of weird and maybe a little less likely to form. So yeah, it makes sense that a 6-member ring would form a more stable ring. Okay, then we also have the Michael reaction. This is kind of a different variation. It's a condensation reaction because we're taking two pieces and attaching them. And the product of a Michael reaction, conveniently, we just call a 1,5-dicarbonyl. So it's going to be two carbonyls separated by, well, we can number them and say it's a 1,5-dicarbonyl. So this is an example of a simple example of a Michael reaction. So the ketone reacts this alpha beta unsaturated ester, alpha beta unsaturated, right, with the alkene there. And yeah, the reagent is base, NaOET usually, or I guess if you have a methyl ester, you'd probably use NaOMe, NaOCH3 as your base, and that takes off the ketone alpha CH, making enolate. Enolate attacks, and then, right, because this thing is an electrophile, it does a 1,4 addition. Yep, and then makes an enolate, and then you need a water step or something, and that gives you the final product. Okay. Anything else about this? Oh yeah, we had that nomenclature. This is the Michael something, and this is the Michael other something, right? Maybe well, obviously nucleophile, electrophile. Another way to say that is donor acceptor. So this is the Michael donor, Michael acceptor. Okay, and that's the product of the Michael reaction. Here's just another example. Okay, so you got a different Michael donor. This is barbituric acid. This is a different Michael acceptor. So yeah, but this is highly acidic, so much more acidic than this because you have the two ketones here. Anyway, the base would take the proton and then it would attack, and then you'd get the product like this. Okay. The Robinson reaction is kind of like a Michael, but it keeps going. It's a Michael reaction that continues after the Michael reaction to do more stuff. Here's a couple examples. You've learned about the Robinson. It's also called the Robinson annulation. annulation means ring formation. So the thing about the Robinson and kind of the requirement is that, because it is a Michael reaction, it's a Michael reaction that more stuff happens after the Michael. And so you have the Michael donor, you have the Michael acceptor. And remember, the kind of the requirement to do a Robinson is that your Michael acceptor, which is this thing, it has to be a ketone, and on the other side of the Michael acceptor, which is this side, the right side, you need a CH, because the CH is going to be necessary for the subsequent reaction. Okay, and yeah, so this has all the requirements for a Robinson reaction. It's a Michael acceptor, it's a ketone, and it's got a CH on the other side. Okay, this one also works. And this is a beta diketone Michael donor. A beta diketone Michael donor. We saw that in chapter 23 actually. Robinson annulation with beta diketones. Both of these work. I say step through, and usually if I was in front of a whiteboard for this, I would step through, but you can do this. It's kind of hard for me doing this by video. Step through this. Remember, these are the 4 steps. First, you do a Michael reaction, and that basically means with a base takes proton, makes an enolate. Now you got an enolate. That's still kind of step A. And then the next step is the enolate attacks. That's also step A. And then thereafter it's proton transfer, re-enolize. And that essentially just means the enolate was on one side, you just move it to the other side, right? So you have a new enolate, and then you're ready for your intramolecular aldol. Okay? So then the enolate from the other side, after these are attached, right? These are attached. And then these are attached. And then you've proton transferred enolate to the other side, and then that enolate is able to swing back and attack the ketone. So then you can see it right there, right? You can kind of see the relationship between what was the Michael donor with what was the Michael acceptor, right? It's the same exact thing on the bottom. It's just you have an extra ketone. And the other difference is this is a less acidic proton, this is a more acidic proton. Okay, we can kind of see the relationship between these molecules. Okay, step through these. Do this yourself. Make sure you understand this. Why didn't the Michael reactions on the previous slide go on to the Robinson? Well, let's go look at those again. These are the Michaels that we just showed a second ago. Well, why don't these do a Robinson? Well, the big issue is you got esters. Esters don't do it. You need ketones. Not only do you need ketones, you also need an enolizable CH on this side of the ketone. Okay? Cool. And then one more, Robinson via retrosynthesis. See if you can step backward and figure out what the fundamental starting materials were. Okay, so the way to do this is apply steps A, B, C, and D, but go backwards. So you envision the alpha beta unsaturated ketone, and then you do the intramolecular aldol going backwards, and you figure out where the enolate was, and you can kind of go back. We did this in the lecture notes. You should review this. If it's unfamiliar, try it. See if you can do it. See if you can go backwards. Okay, CC bond cleavage. All right, so CC bond cleavage. Yeah, you don't know that many ways to cleave carbon bonds. Maybe the first one you learned was actually from organic. You learned it in organic 1, and then we talked about it again in organic 2. Osmolysis, which cleaves alkenes, right? And it gives you carbonyls, ketones or aldehydes. So this alkene is cleaved to give a aldehyde and a ketone. And this is technically something you kind of did in organic 1, so mechanistically not that interesting. The reagents are O3 and then zinc acid or zinc acetic acid. Probably not going to see this well, it was technically an early reaction you learned. Much of the cumulative final is going to be, there's a little bit more of an emphasis on newer stuff. But yeah, this, trying to grasp the full picture of organic chemistry, this was a way to cleave bonds, right? Maybe the first way you've learned to cleave a carbon-carbon bond. Decarboxylation is a kind of a new one. Malonic and acetoacetic ester synthesis show this way of cleaving off CO2. Remember the basic idea of it. This is an example of a malonic ester synthesis where you start with acetoacetic ester. Malonic has 2 esters. The acetoacetic one has 1 ester. Okay, and yeah, so attach a R group, benzyl in this situation, and then it's like acid. Usually, acid and heat causes the hydrolysis of this ester, and then you go from a beta keto ester to a beta keto acid. The beta keto acid is unstable, loses CO2, and you get a ketone. So this falls off, and the end result is now you just have a ketone with how many carbons? 1, 2, 3, 4 carbon chain. 1, 2, 3, 4 carbon chain, and then the benzene and CO2. Hoffman rearrangement was another example of a reaction where CO2 is lost. And so you have a primary amide. This is definitely a 2-star one, kind of cool reaction where base takes proton and it's like Br2, right? NaOH and Br2, and so you deprotonate and then brominate the nitrogen, and then you take off the other proton, and makes that nitrene thing. Remember the nitrene? The nitrene was like a nitrogen with 2 lone pairs and a neutral charge. And then this thing migrated to the other side, and eventually you lost CO2. I'd review that reaction, review the mechanism. Okay, functional group interconversion. So there's a lot of these ones, just kind of miscellaneous reactions that we've seen, and we'll go through them and as part of this review process. Okay. Oxidation reduction, and then alcohols and alkenes, alkynes, etc. Okay, so this just kind of reviews all of the oxidation and reduction chemistry that can happen for a primary alcohol that we've learned. Primary alcohols can be oxidized to aldehydes with PCC, and they can be further oxidized to the carboxylic acid with CrO3. But if you take a primary alcohol, you can go and you react it with CrO3, it goes all the way up to the carboxylic acid. Tollen's reaction or Tollen's reagent was a way to go only from an aldehyde to a carboxylic acid. It's kind of an obscure oxidizing agent, so it's not that critical for us, but it is selective. It doesn't react with with alcohols. It only goes with aldehydes. Okay, and then kind of go in the other direction. You cannot go from a carboxylic acid to an aldehyde directly. There's not a easy way synthetically to do that. You could do it as a 2-step process, though. How could you do it as 2 steps? Well, we know that if you make an acid chlorides have a reagent. There's a special H- reagent that goes to the aldehyde. You can also turn it into an ester, right? You can also turn it into an ester, and esters react. You have a special H- that will go from ester to aldehyde. You can also, if you want to go from carboxylic acid to aldehyde, you can also go all the way down to the primary alcohol using lithium aluminum hydride, and then just do a partial oxidation. So that's another way you could go. You could go full reduction, partial oxidation to the aldehyde, and then from the aldehyde you can go to the alcohol with NaBH4. So these are all just hydride reagents, nucleophilic hydride. NaBH4 we often just do as a single step with just methanol as your proton source. Okay, and And then we also have this kind of weird reduction method where you have an aldehyde, or also ketones, that reduces off the oxygens altogether and makes an alkane. So the Wolff-Kishner reaction, remember that? That's a good 2-star one. That yeah, you make a hydrazone. It's hydrazine, NH2, NH2 attacks, and you make the hydrazone intermediate, and then it falls apart, and you make the alkane. So this completely wipes away a ketone or aldehyde. The other trick now also is you can make a thioacetal, so the sulfur-sulfur thing, and then you can treat it with H2 rainy nickel, which will remove it also. So that's kind of a way to go from an aldehyde to a complete non-functional group. Just wipe it away. Okay, so recall the indirect ways of converting an acid to an aldehyde. We just did that. This is kind of a similar scheme, but this is sort of assuming we're starting with a secondary alcohol instead of a primary. So we can go from a secondary alcohol to a ketone using PCC or CrO3, and that can't go any further, so it's just a single-step oxidation. And then you can reduce that with NaBH4. Of course, you can use lithium aluminum hydride as well, but that's sort of what we call it overkill. It's a little unnecessary because this is fairly mild and not going to catch the lab on fire. But LiAlH4 you have to be very careful with, and it will catch the lab on fire if you mess that up. And then, of course, with ketones, you can also oxidize a ketone to an ester, and that's called the Beer-Villiger oxidation. So this is an oxidation condition that actually goes from ketone to ester. And we did the mechanism of that. Yeah, we did learn that mechanism. And then the ketone can also be reduced all the way down to the alkane. Same thing, Wolff-Kishner or the thioacetal rainy nickel method. Okay, and yeah, some semesters we don't teach the Beer-Villiger, but you did learn it this semester. Pretty cool mechanism how it worked also. Okay, along these lines, when we talk about oxidations and reductions, these are mostly all reductions here. But think about an amide, a primary amide. We can reduce a primary amide to an aldehyde. And that kind of just, we use dibol. And so dibol is a H- that attacks, and then essentially just kicks off just the amine. So dibol is a partial reducing agent. Also from the aldehyde state, we can turn aldehydes into amines, and that's reductive amination with NaCN-BH3. So you can do this with like ammonia, NH3 and NaCN-BH3. And that will reduce the aldehyde to an amine. Of course, amides also can be directly reduced all the way to the amine just using lithium aluminum hydride. All right, and then nitriles also can be partially reduced to the aldehyde or fully reduced to the amine. Nitriles can be partially reduced or fully reduced. And then we also know about azides, and we learned about azides as a way to make amines, and that's using you can synthesize the azide from like an SN2 reaction, and then lithium aluminum hydride will reduce the azide and get you to the primary amine.